we want to when we are dealing with the CFD means there is kind of fluid is involved. So we have to calculate the fluid property at different node. Okay, the fluid property are modeled empirically. Basically, here is term empirically means there is kind of some relation. Okay, we want to calculate the density at so many of points. So how density will be work? So basically, density is a function of temperature. Okay, so we want to calculate at each node. Node means for different point. Okay, simplifying assumption are made in order to make the problem traceable. Like the steady state, incompressible, and viscous at 2-dimensional or 3-dimensional. This totally dependent to us which kind of model we are taking. Now, how to apply CFD in different application? See, so I think some guys from the mechanical and some chemical and some electrical. So see, appropriate initial and boundary condition are provided for the problem. For example, I am taking a mechanical example, for electrical, then I will take the chemical also. Suppose we want to calculate the temperature distribution along the length for any composite material, yeah, maybe composite slab. So what we have to do? We have to give the boundary condition, what is the left side of temperature and what is the right hand side of the temperature. So we can easily calculate throughout the temperature distribution. And we can also calculate what is the temperature distribution along the length and time. Okay, similar manner in electrical, we are dealing with the motor. So in motor case, we want to calculate the modal analysis. Modal analysis, basically, we will see the failure, frequency of that particular. We can apply that thing. Okay, and similarly, chemical reaction we want to see, and chemical. So what we will do? How much means gases incoming and what is the gas is going out, and how much consumption of maybe stored by gas inside the whole of the domain. So these kind of the example, by applying initial and boundary condition, we can apply the CFD. Okay, so basically there are 3 steps. One is the pre-process, second process is a solver, and third process is a post-process. Okay, so basically in a pre-process, we are just providing the modeling, geometry of that and boundary condition, all that. And solving process, we will provide a solver, which kind of solver we want, either pressure based or maybe density based, like that. And post processor, we will just obtain the result. So we have to interpret that result, which kind of result we are getting. Sometimes we are getting the good result, sometimes we will get the bad result. But we have to understand the physics behind that so that we can correctly identify the correct answer or result. Okay. So CFD applies numerical method called discretization. Here is the word discretization, means very small. We are talking about the very small quantity. Means like we are making a maze, maybe you know that. So discretize is we are just taking a small difference between 2 points. Okay. To develop approximation of the governing equation of fluid mechanics and fluid region of interest. The solution is process to extract quantity of interest, like what we want to obtain, either strain, or maybe lift, drag, torque, heat transfer, separation, pressure loss, etc. Okay, it's totally depend on us what we want to output. Now, discretization. See, in this diagram, we can easily see that is the visible arrow is. See, there is a small sink. So basically, this is the discretization element. We can say this is the element also. Okay. So domain is discretized into a finite set of control volume or cells. The discretized domain is called the grid or the maze. Basically, this one element of this. Basically, this is a very small quantity. Yeah, we can say a small volume of particular domain. So generalized conservation, transportation equation for mass, moment, and energy, etc. are discretized into algebraic equation. Okay, beta. So all equations are solved to render flow field. So basically, with the help of solving combined equation, mass, momentum, and pressure, that will give the final answer of particular domain. So Here we can see that all are the discretized point. Okay. Now, numerical model setup. After discretization, we have to move in a numerical model setup. What we will do there? So basically, for a given problem, we will need to first select the appropriate physical model. Which kind of model we are taking? Either laminar flow, or maybe turbulent flow, yeah, maybe friction, yeah, maybe energy we have to on, like that. So based on that, we have to design the after first choosing the model, we have to decide the material of that particular geometry. That is solid, yeah, maybe fluid, yeah, maybe mixture of all these things. Next, prescribe operating condition. Here is a operating condition means we have to provide inlet and outlet and wall condition. It's totally dependent what we are giving. Okay, then after that, prescribe boundary condition at all the boundary zone. Okay, next set up the solver control and set up the convergence monitor. So these all three is the very important. Boundary condition at all boundary zone. Okay, set up the solver. Basically, in this point, we will provide the solver. Okay, if we are using the programming, so we have to write the solver like TDMA. Okay, yeah, Gauss elimination method. Whatever we will use in solving the matrix, we can use here. But in a commercial software, there is already given inbuilt in the software. We have to choose from that particular software. Like we are using the ANSYS, so we have to choose maybe PISO, simple, yeah, different kind of K epsilon, yeah, K omega model is given. Okay, and when we are monitoring the result, that result is whatever they are calculating, that is converging or not. In a bit of when we are dealing with the CFD, yeah, we are applying the CFD in a particular, we have to check the three things. One is the convergence, second is the stability. Okay, both things we have to check this. If that will be not converged, means we are getting the false result. Yeah, maybe some garbage result. That is not useful. See, application of CFD. See, so application of CFD is in a various field. Either we can use an spray dyeing, freezing dyeing, banking, bioreactor, pressurization, sterilization, heat exchanger, mixing, chilling, and refrigeration. So many. Either we can say every branch can use the CFD. Either I'm saying like that. Yeah, mechanical, electrical, chemical, civil, biomedical. Everyone using nowadays. Everyone using the CFD. Basically, this is the tool. So now come to the fuel cell technology and fuel and their application. So basically, I have used this one. Reason behind ki you all guys are pursuing MTech in a chemical, yeah, and this subject is in your curriculum. Am I right? I think.
Sorry, I'm taking energy systems.
Okay, that I am taking some of the example from the fuel cell, so that I will explain some terms so that you will understand actually what's going on here. See, so basically in the fuel cell, okay, see, maybe enough. Some slide is maybe okay. Now I will go back. First, we have to understand a fuel cell is the energy conservation device. See, what is a fuel cell? So basically, a fuel cell is an energy conservation device that convert the chemical energy of the fuel into electrical energy. Okay. So basically, what is the fuel cell is doing? Some of the chemical reaction is happening, and they generate the electricity, and that electricity is used to drive the motor, basically in a EV. See, okay, so basically in the fuel cell we can say battery mostly used in a different kind of application. So here fuel cell technology or fuel and in application is basically used on a various kind of things, either a stationary part, yeah, maybe some movable part, yeah, maybe sometime stationary, sometime movable. So here is the one of the glimpse I have mentioned. Basically, I'm not citing this. Basically, I am taking some images from the Google, this one. So see, types of fuel cell: AFC, alkaline fuel cell; DMFC, direct methanol fuel cell; ST, TMFC, basically high temperature proton exchange membrane fuel cell; FCFC, MCFC, basically molten carbonate fuel cell; and then PAFC, phosphoric acid fuel cell; and PMFC, proton exchange membrane fuel cell; SOFC, solid oxidized fuel cell. So these are the basically a classification of fuel cell. Okay. So here from this diagram we can easily understand the where we will use different kind of fuel cell and particular application. So see, in the stationary, basically residential or industrial, we are basically using the battery for the electricity. What we are doing nowadays, if suddenly power cut is happening, we are rely on the battery. So which kind of battery? So basically maybe sometime solid or maybe sometime liquid type. So like phosphorus type we will use. For transportation, nowadays most of the vehicle is converted into the electric vehicle. So how electricity is generated? Basically we are using the battery. So either in road transportation, marine and air. Okay, some of the aircraft like a drone. Okay, basically powered by the battery. Okay, some fuel cell also used in a portable application. Here also we can see as to basically hydrogen. We are talking about the hydrogen fuel cell. Here is a methanol and biogas, different kind of is saying. Basically in this, what is the major contribution of gases? So hydrogen, basically TM or AFC is categorized in the form of hydrogen fuel cell, and DMFC basically categorized in the methanol, yeah, maybe we can say ethanol part, and sub PAPC, PM, MCFC and SOFC that come under the biogas and natural gas, gasoline and coal. Basically that is come from this. Okay, so based on that, typical fuel cell technology by application. So here we can see which kind of power consumption is in the different kind of power consumption. We can use the different kind of battery for the portable. So we can use 5 watt to 20 kilowatt of power. Okay. So typical technology, what we will use? We will use PMFC, basically proton exchange membrane fuel cell. I will explain in the next slide all these things. So for example, comprehensive boat lighting is small personal electronics. Here is also transportation 1 kilowatt to 100 kilowatt. Basically in transportation, we will use 1 kilowatt to 100 kilowatt of the battery, which have power range. So in this we can use the PMFC and DMFC. And a stationary application, in a stationary application, basically power is a very high, most probably very high. We cannot say that only high power is required. So basically in the stationary 0.5 kilowatt to 400 kilowatt is required. In this we will use MCFC, PFC, SOFC and PMFC for large stationary combined heat and power and then uninterrupted power supply. See, PEMFC, polymer important. Most of the battery basically use PEMFC. Okay. And most of the research is going on this particular cell. And one of the major drawback of this is a critical heat dissipation and conversion of water in this. So see, solid power, that is called PEM, also referred to a proton exchange membrane fuel cell. Because of their low operating temperature, about 80 degrees centigrade, they can start quickly and sustain less wear. Okay, so PEM fuel cell normally employ a platinum or platinum alloy as a catalyst, so that reaction will be fast and only need hydrogen, oxygen, and water to the function. Okay, only three things. They are renowned for the being both compact and having a high power density. Okay, the PEMFC is one of the most promising fuel cell type, especially for use in a vehicle. They are appropriate for quick startup and shut down cycle. So see, in this diagram, we can easily see as the JDL and hydrogen. So basically, one is the anode, another is the is coming and just broken down the hydrogen ion plus 4 electron is releasing, and here is the combining O2 plus 4 electron and just making twice O2. So basically, after combining this, they will be making H2O. Okay, so here by combining this, so basically with the help of this, they will generate the electricity. Okay, but their proper heat distribution is very difficult. So still research is going on. First thing. Second thing, most of the researchers try to optimize the generation of electricity through the this means PEMFC. Okay, a proton electro membrane fuel cell. Now another one is alkaline fuel cell. In similar manner, here we can see the electrode in these cells is a aqueous solution of sodium hydroxide, or we can say another thing is the potassium dihydrate. AFC typically function at a temperature below 100 degrees centigrade. That is working temperature is 20 degrees centigrade, primarily powered by the hydrogen gas and oxygen. So under some circumstances, other material like zinc and aluminum may also be employed in this application, like the American Space Center orbit have made use of AFC. See, so what is happening here? See, and also here is hydrogen is coming in the side. This see, and also anode and cathode is also there. So by combining this, they will generate the some basically electron will be losses are moving in this, and they will produce the electricity that is further used in this fuel cell. Also critical part is the proper heat dissipation and formation of water. By combining this, these fuel cells have an efficiency of roughly 40 to 40% and operate between 150 to 200 degrees centigrade. Okay, the phosphoric acid is electrolyte. At high temperature, they can tolerate fuel impurity, but at lower temperature, they can damage by carbon monoxide. Okay, so basically where a heavy work is going on, yeah, maybe we can see it where a highly power is required, like hospital, lodging facility, workplace, airport, and educational institute use PFC. Most of the batteries in the institute is used by a PFC. Now, why CFD is used in a fuel cell analysis? That is a more important rather than we are understanding the basic thing. Well, so basically, we want to manage heat dissipation, proper heat dissipation in the fuel cell. So heat management poses a significant challenge in operating hydrogen fuel cell because it directly affects cell performance and efficiency, particularly in air-cooled proton electrolyte membrane fuel cell. Okay, as well as in hydrogen fuel cell also. Okay, so if the heat generated by the fuel cell electrochemical process not effectively controlled, it may harm its component or worsen its performance. So that's why we are trying to use CFD so that we can understand the basic phenomena and understand how water is accumulating inside the chamber or maybe inside the enclosure. Therefore, it is essential to have a thorough understanding of the thermal behavior and heat source within the fuel cell system. Okay. A thermal analysis tool can address this issue quickly and help predict airflow, temperature distribution, heat transfer, owing to its accessibility, scalability, and capacity to run multiple thermal simulation in parallel. Basically, what we are trying to do, we want to understand how the temperature is distributed throughout the enclosure. Either we can say on the anode, on the electrode, how much water is accumulated in the enclosure during this, how much gases is accumulated inside, yeah, how much electron is consumed by the gases inside the chamber. Okay, so the stake, the anode and cathode gas supply substance and then trial gas exhaustion subsystem can all be included in the simulation overall model of the PM fuel cell system. So basically, whenever we are trying to perform the experimentally, so that will be very cost consuming. So first we have to check the outcome of this by applying the CFD, how that behavior is going on. Once we will do the CFD, we can accordingly we can model the, maybe perform the experimentally. So basically CFD give us the ideal condition. Okay, maybe by manipulating with our boundary condition, we will mimic that model similar to the experimental model. Okay, so now I am taking a two case study for this. So one case study one is the objective of this case study is to understand and simulate the proton exchange membrane fuel cell using the add-on module PEM fuel cell module available in ANSYS Fluent to verify the result obtained using the CFD simulation. So basically the current density versus voltage curve, IV curve was compared with the experimental work. Okay? So basically first we have to model similar geometry in the ANSYS, basically in the design, we can say design modular button. Okay? So basically, in my system ANSYS is not installed, so I am unable to show you how we can apply this. But with the help of this stages, I will explain. See, so first we have to model this one. Okay, so from this diagram we can see this is the gas chamber, this is a cooling chamber. Here is also anode. Similarly, anode gas diffusion layer. Okay, that is called GDL, gas diffusion layer. Further, anode catalyst layer. Okay, electrolyte membrane, which is mentioned in between that. Further, here similar thing is going in the anode section, so we have to apply in the cathode section also, like cathode catalyst layer. Okay, cathode gas diffusion layer, then cathode current collector and cooling channel. Okay, beta. So we have to model like this. So so basically it is a compact clean run at a low temperature. Basically we have already, I have explained, basically PM fuel cell is working at the 80 degrees centigrade. So basically that is the mention less than 100 degrees centigrade, and its permit an adjustable power output, and it can be start relatively faster and also shut down faster. So in this electrochemical reaction will be happen. So what is the electrochemical reaction take place in this? So in the anode and cathode triple phase boundary, also called the catalyst layer at the anode TPB, triple phase boundary. So see, here is the H2 is equal to twice basically hydrogen is broken down in a ion, basically losing the some electron at the anode. Similarly, here is I am mentioning half, basically 1 by 2 O2 plus twice hydrogen ion plus 2 electron. By combining this, they will make the H2 at the cathode, where TPB. So electron produced in the anode travel through an external circuit to the cathode, while proton, basically hydrogen ion, travel from the anode TPB to the cathode TPB through the membrane, thereby forming an electric circuit so that the current will be produced. These are the input we have to give in, okay, during the modeling. what is the C? Here I am mentioning gas channel length. All units are mm. So I am giving value 10. Okay, this one. Gas channel width 1 mm. Gas channel height 1 mm. Current collector thickness 2.5 mm. And gas diffusion layer thickness 0.00254 mm. And catalyst layer thickness 0.0014. Membrane thick range 0.051. Cell width 2 mm. And overall height is 5.129 basically this one. So all this value is incorporated in this. Okay. So when we are trying to solve this kind of problem in an ANSYS, we have to first make the design. So how we will make the design? So basically there are two options. One is the design modeler, another is the space claim. We can use both. Reason behind in both, we have to only draw the geometry. Okay. So either we will draw in a 2D form or maybe 3D. Yeah, we can also use another CAD model, like we will use the SolidWorks also, yeah, maybe Fusion 360. So that first we will make the design of that particular, and just we have to convert in the IGS file, and just after taking the IGS file, we have to import. Okay, import in the ANSYS. See now. So after designing, this one is the basically designing, and after designing we have to create the mesh, means discretize this particular part. So in this we are basically converting our 2D or maybe 3D model in a very small element, or maybe we can say element and node, so that we can calculate approximation of particular value. Okay, so when we have generate the mesh, we have to need to apply the initial and boundary condition. Okay, so after applying the initial and boundary condition, we will get the some result. Okay, so here is showing current density versus voltage curve, IV curve. So basically these are the experimental work done. Now see, so after applying the boundary, I am not showing here the boundary condition as well as solver. Okay, otherwise we just basically we can directly take the solver from the ANSYS. Okay, so based on that we will see here, just to give me a moment. See, so basically this is the contour plot of hydrogen and oxygen distribution in the fuel cell in this. So see what is happening. What is happening? See, just give me a moment. Something. What was? Okay. So basically, what is happening, beta, in this? So mass fraction of H2 and O2 decrease as it flew from inlet to the outlet side of the flow channel. So basically what is happening in this zone? When we are entering the hydrogen and this side from the oxygen, to decrease that it flew from the inlet to the outlet. Why this is happening? So due to gas are consumed inside the PMFC to generate current and water as the output. So basically, from this contour plot, we can understand. Now, basically, this image is not clearly visible, but from the diagram, we can see here is a blue line showing the very less value. A red is giving the higher value. So see, at this particular point, this one is the higher, but now we can see that we are moving in the right hand side from this direction. See, their color will be changed. Color is the continuously changing. They are red now, orange now, yellow. Okay, so basically their value is decreasing. Okay, why this is happening? To most of the gases consumed by inside the chamber, so that they will combine to form the electricity, because combination of the electron and some combination of water plus hydrogen plus O to make the water. Okay, so basically we try to minimize that formation of water during that reaction. What is happening when water is accumulated too much? Anyone from the class? What will be happen? Any idea, beta? See, basically in the enclosure there is a customized area. We are trying to escape that water also. Means there is also a drainage so that the water will accumulate and go down. But somewhere it is not possible. So what will be happen? Their accumulation of water will be increased and then their reaction will be decreased. So electricity will be not produced whatever we want. Means that will not give a desired output of the electricity. So our research will be waste. So that's why researchers try to optimize this phenomena. Now I have taken another case study for CFD simulation of PEM fuel cell performance effective state and separating flow field. Basically another things model here. So a comprehensive non-isothermal three-dimensional model has been established to investigate the performance of proton exchange membrane fuel cell with state and separate flow field. Okay, two flow pattern including co-current and counter current are considered for all the flow in cell. Basically, two types of flow are considered in this. Okay. Next is oxygen and hydrogen mass fraction distribution, current density and temperature distribution has been determined. Basically, in this study, we are trying to find out oxygen and hydrogen mass fraction distribution from the cell. Second thing, current density and temperature distribution from the process. How much current, yeah, maybe we can say how much electricity is generated when the reaction will be happening. Okay. As well as we are also checking the temperature distribution. Suppose that if temperature will increase too much, like 100 or maybe 200, so their membrane will be get easily damaged. So we are trying to optimize temperature also, or maybe we can say one of the challenging tasks is the critical heat dissipation in the